Deep shaft constructors often encounter difficult geological conditions, such as high groundwater pressure, combined with layers of hard and soft material. There is an increased requirement to avoid dewatering during construction of shafts in order to avoid the associated settlements, which can affect a wide area. The following animation shows how the Heron Connect VSM shaft sinking equipment can install shafts quickly, safely, and economically in difficult ground conditions and in inner city areas with limited construction footprints. The initial section is excavated, 1 to 2 meters in depth, and a support concrete ring beam is installed. It acts as a guideway and absorbs the forces from the shaft sinking process. The first segments of the shaft are assembled and lifted in place. The bottom segment ring has an integrated steel edge, which acts as a cutting knife during the shaft sinking. Strand jacks are installed on the support concrete. Strand wires are connected to pockets in the cutting edge. The numbers of strands corresponds to the total weight of the shaft. The shaft is now held in position by this compact strand jack system. Preparation for the machine installation starts by using a dummy frame to position the brackets for the machine arms, which are then welded to the steel plates already cast into the concrete segments. The VSM machine is assembled with the correct arm length to suit the shaft diameter. And then lifted into the shaft by a mobile crane and mounted onto the brackets. The rest of the shaft sinking equipment can now be installed. The 3 winches are used to lift and lower the machine, i.e. for regular maintenance during shaft sinking, as well as to lift it out when the shaft is complete. The energy and supply lines provide the machine with all necessary power, fluids, and communication. This is an example of a complete site setup. All operations are powered and controlled from the container on the surface. Stored data, together with the position of the cutter boom, is shown on a graphic display, giving the operator full control of the excavation and sinking process. The cutter boom can either be controlled manually by the operator or set in automatic mode for cutting the set profile in the required section. The shaft is kept full of water during sinking to balance the level of the groundwater table in the surrounding geology. In addition, the water itself is used as the transport medium for the excavated ground. Various depths of the groundwater level can be handled. The flexibility of its telescopic arm rotation and slewing movements allows the cutter boom to work in shafts with inner diameters from 4.5 meters and outer diameter up to 18 meters in water depths up to 80 meters. The cutting arm moves radially from the center to the outside of the shaft. In soft soil, the cutting edge on the shaft is able to trim the excavation as it sinks into the ground. The cutting speed and the movement of the boom can be varied to achieve the best excavation rate. When it's necessary to excavate under the cutting edge, such as in hard soil, the machine can be moved to a lower position in the bracket to extend the reach of the boom. Where hard soil is encountered, the machine cuts out to the programmed limit all around the circumference before the shaft is lowered. In rock, this controlled descent allows all of the cutting edge to be cleared before lowering. This avoids trapping the cutter boom or deviations in the shaft vertically. A slurry circuit transports the excavated material from the shaft to a separation plant on the surface. The cutter drum cuts and crushes the material to a granular size that can be handled by the integrated centrifugal pump. In sticky ground conditions, an additional high-pressure feed line can be used to clean the cutting drum. The separation equipment is selected to suit the local soil conditions. As the shaft sinks lower, precast concrete segments with rubber sealing gaskets are bolted in place on the top of the shaft. Excavation, shaft sinking, and construction of the next ring can take place continuously. The molds for the segments are also supplied as part of the shaft sinking equipment package. Segment dimensions are designed to suit the shaft's purpose. The daily sinking production is in a large range from 1 to 5 meters, depending on the diameter, geology, and working hours. As an alternative to constructing the shaft from individual segment rings, in situ concrete can also be used. Formwork, designed for the shaft diameter, is used to concrete the shaft lining in lifts of about 2 meters in height. The sinking process itself is the same as for shafts constructed with segments. This can be an advantage if the shaft is to be used for launching tunneling machines. The shaft wall can then be prepared with a built-in launch eye to exactly suit the tunneling equipment. An automatic bentonite lubrication system reduces friction between the shaft exterior and the surrounding ground during shaft sinking. The total number of nozzles is designed to suit the soil conditions. When the shaft reaches the final depth, the VSM machine is removed and the concrete base block is cast. Afterwards, the bentonite in the annulus around the shaft is displaced by grout injected through the bentonite nozzles. Once the grout gains sufficient strength, the water is pumped out. The shaft construction has been completed without affecting the groundwater or the surrounding soil. The shaft is now ready to be used. Up to this point in time, Heron Connect VSM technology has been used to construct shafts for several different types of applications, with many more planned in the future. For ventilation and emergency shafts for traffic tunnels, such as those found in metros and railways. For underground storage, for example, goods or fluids. For TBM launch and reception shafts. For sewage collector systems. For future underground parking systems. The compact design, with the possibility to separate and place the equipment at different locations during construction, production speed, and economical application are all reasons for choosing the Heron Connect VSM technology. Heron Connect is continually developing the VSM technology in order to expand the use cases while ensuring a safe and environmentally friendly operating environment. The following computer animation shows the way earth pressure balance shields work. Taking as an example the Heron Connect EPB shield used for a subway construction project in Barcelona. As part of the extension of Subway Line 9, the machine S442 excavates a 3.6-kilometer-long section between the subway stations Gornal and Zona Universitaria. The tunnel route crosses beneath Barcelona's historic city center, densely populated residential areas and roads. In order to avoid any damage to the sensitive buildings, subsidence, heave, and vibrations must be avoided at all costs. In addition, The impact on traffic above ground must remain as small as possible. The S442 is a classic EPB machine with an outer diameter of 12.06 meters and a total length of 95 meters. With its rotating cutting wheel, the tunneling machine breaks the material from the tunnel face. The material is then transferred to the belt conveyor system in the rear of the shield via a screw conveyor, while the hydraulic cylinders press the machine forward continuously. The reinforced concrete segments, known as lining segments, are installed under the protection of the shield skin. When the ring building has been completed, the machine can push itself against the new tunnel ring and drill further into the soil. The 83-meter-long backup accommodates all logistic facilities necessary for the operation of the overall system. The working method of an EPB shield is basically made up of two phases, the tunneling phase and the ring building phase. During the tunneling phase, the cutting wheel, which rotates at a speed of up to 2.7 revolutions per minute, is pressed against the tunnel face with a pressure of up to 400 bar by means of hydraulic cylinders. 24 hydraulic motors drive the cutting wheel via a gear rim, developing a drilling torque of up to 38,000 kilonewton meters. Under this high pressure, the disc cutters and cutting knives made of high-strength steel loosen the material at the tunnel face. If necessary, the soil can be conditioned with water, bentonite, or foam using the injection systems located on the backup. With the help of nozzles integrated into the cutting wheel, the corresponding conditioning medium is injected into the soil, which is pressed into the excavation chamber by the existing earth and groundwater pressure. For shield tunneling in non-stable soils, a loss in stability at the tunnel face is compensated by creating a support pressure. In the case of the earth pressure balance shield, the soil which was excavated by the cutting wheel is used to support the tunnel face. In order to reach a state of equilibrium, the support pressure is transferred by the hydraulic cylinders via the bulkhead to the soil, which avoids an uncontrolled penetration. The soil prepared in this way can now be transported from the invert area of the excavation chamber to a belt conveyor by a screw conveyor. The screw conveyor is driven by two hydraulic motors which have a power of up to 400 kilowatts. The quality of the soil taken from the excavation chamber is regulated by the screw conveyor's rotational speed, which is matched to the advance speed. The aim is to maintain a state of equilibrium between the quantity of soil removed by the screw conveyor and the quantity of soil accumulated from the shield's tunneling process. This guarantees optimum support for the tunnel face. The system must be able to react flexibly to the permanently changing geological conditions. Therefore, the current state is continuously controlled with the help of pressure sensors, by measuring the cutting wheel torque and the screw conveyor torque, and by monitoring the excavated material. When the tunneling phase is completed, cutting wheel and screw conveyor are stopped. Now the ring building phase starts in the shield area under atmospheric pressure conditions. A complete tunnel ring consists of several segments, called lining segments. These prefabricated reinforced concrete elements are produced with millimeter precision in a factory which is especially installed above ground for this purpose. Following quality control, they are then transported into the tunnel by mine cars. In the front section of the backup, the lining segments are lifted individually by a special transfer crane. It lifts them onto the segment feeder which transports the elements to the front of the tunnel. Here, The heavy ring segments are picked up and positioned by a hydraulically controlled crane arm, called the erector, using vacuum plates. The erector is installed on 2 rails and can be moved, rotated, and telescoped. Each completed tunnel ring consists of several segments, 2 lateral elements, and the key segment, which is installed last. The positioning of the segments always follows the same routine. The erector lifts the stone from the segment feeder. The hydraulic cylinders are then retracted from the corresponding installation point. The segment is positioned precisely, holding sight contact next to the previous installed ring, using a remote control. Now the hydraulic cylinders are extended again to secure the segment in its position and to subsequently bolt it into the previous ring. During this process, machine and tunneling personnel are protected by the shield skin against the earth pressure and any possible groundwater. In this way, the lining segments are installed on each side alternately. The key segment, with its tapered sides, is slotted into position last and distributes the loads in the ring, completing the ring building. Subsequently, the next tunneling phase can start. The end of the shield, the so-called tailskin, is equipped with a circular tailskin sealing. This provides a seal between the sealed structure of the shield machine and the segment ring. This in turn guarantees the necessary sealing between the interior working space and the exterior earth pressure. The remaining annular gap between the outer side of the lining segments and the soil is continuously filled with grout via injection holes in the tailskin or in the lining segment in order to provide a bed for the tunnel tube and to stabilize it. Each individual tunnel ring is constructed in a slightly conical form. This means that curves can be constructed along the tunnel route by changing the installation position. A time-lapse clearly shows the 2 working phases of the TBM. The tunneling phase and the ring-building phase alternate continuously. In this way, the tunnel grows ring by ring. Under optimum conditions, up to 350 meters of tunnel can be constructed in 1 week. This includes the removal of up to 40,000 cubic meters of excavated material and the installation of far more than 1,000 lining segments. Complex logistic solutions are required to deal with such quantities of material. The 83-meter-long backup of the S442 tunnel boring machine accommodates all the facilities required. With each advanced movement of the shield skin, the backup is pulled behind on wheelhouses, which brace against the tunnel wall. Among other things, the steel structure accommodates hydraulic power units, pumps, switch cabinets, ventilation systems, laser instrumentation, and storage containers for soil containers. In addition, logistic solutions for the delivery of the lining segments and the removal of the excavated material are located here. All important data and up-to-date tunneling parameters are gathered together in the central control cabin. There, they are visualized on monitors and made available to the machine operator. The operator can monitor the largely automated process and intervene if necessary. In the case of EPB machines, the excavated material is mostly removed by belt conveyors. The core components of such systems are the machine belt, the cross belt, and the tunnel belt, which can measure up to 30 kilometers. The machine belt and the cross belt are 2 separate short conveyors, which are permanently installed on the tunnel boring machine. The tunnel belt takes up the excavated material from the cross belt in the backup area and transports it along the total tunnel section to the launch shaft. The front section of the tunnel belt is also permanently mounted on the backup. The rear part is statically mounted on the tunnel wall and is continuously extended during the ring building phases to match the growing conveyor distance. In order to compensate for the increase in the conveying distance, a special belt storage system is installed at the launch shaft, which releases the extension of the tunnel belt as required. The cutting tools must be maintained or replaced in regular intervals, depending on the hardness and abrasiveness of the geology. Sensors are attached at the tips of some tools, which trigger an alarm in the control cabin when a certain degree of wear is reached. If a tool must be replaced, the excavation chamber is partially emptied. At the same time, the cavity in the chamber is supplied with compressed air, if necessary, to stabilize the tunnel face. Then, the excavation chamber can be accessed through a manlock to carry out maintenance work or to replace tools. A disc cutter is exchanged in 3 steps. Initially, the quick-release fasteners are loosened. Subsequently, the disc cutter is pulled out of its support with a special tool and, in a 3rd step, replaced by a new one. Traditionally, earth pressure balance shields made by Heron Connect are in their element in cohesive soils consisting of clay and silt with low water permeability. Moreover, loose soils consisting of sand and gravel and unstable rock can also be successfully mastered with the EPB technology.